Now let's move on and talk about hypothesis testing. So hypothesis testing is simply another form of statistical inference. A hypothesis is a claim or a statement about a property of the population. And a hypothesis test, or a significance test as we call it sometimes, is a standard procedure for testing claims about properties of a population. Hypothesis tests allow us to sample data from population and then infer something around the whole population. So that's a really important idea because essentially it tells us that if you want to know something about the population, you don't need to go out there and ask or inquire every single person. You can just collect a sample and do the same. So that's the whole premise behind statistical inference. So this is the general framework for conducting hypothesis testing. There are two hypotheses, the null hypothesis and the alternative hypothesis. So we begin with the assumption that the null hypothesis is true. The goal is to determine whether there is enough evidence to infer that the alternative hypothesis is true. And there are two possible decisions, that there is either enough evidence to support the alternative hypothesis or that there is not enough evidence to support the alternative hypothesis. So it's a binary thing, it's either or. Very important note here that we never say that we accept the null hypothesis. What we say is that we reject the null hypothesis in favor of the alternative hypothesis, or that there is not enough evidence to support the alternative hypothesis. So there are some epistemological reasons as to why this happens. In general, you can treat this as standard phrasing. Basically, we assume that we can't really know whether a null hypothesis is true. However, we know when we can reject it. So this might be a bit confusing. Again, it relates to epistemology, which is basically philosophy of science. So just take this as it is. I mean, if you write, for example, an academic paper and you have to report results, you have to report them in this way. So hypothesis tests, since we're examining population parameters, they can be examined on any parameter of a population or on differences between populations. So let's see this example. Let's say that a company has a 10% market share and launches a marketing campaign. So it wants to assess whether the market share has increased after the end of this campaign. So think about for a second how you could form this as a hypothesis test. What's the population of interest and what is the parameter of interest? We'll see the answer shortly. Example 2. A bottling machine is set to automatically fill each bottle with 355 milliliters of a soft drink. So you want to do a quality control of this machine, and an inspector examines a random sample of the newly filled bottles. So what's the hypothesis here, and what is the statistic of our interest? Think about it again and we'll see the answer shortly. So for the first example, the market share example, the parameter of interest is the true proportion of customers who are going to purchase the products after the marketing campaign. For the second example, the parameter of interest is the true mean volume per bottle. So before we formulate the null and alternative hypothesis for the two examples, let's do a quick recap of what the null hypothesis and the alternative hypothesis are about. So the null hypothesis is a statement that the value of the parameters of interest for the population are equal to some value. So the null hypothesis essentially is a construct that says that nothing is happening, there's no difference or no change in a population. And as I mentioned earlier, when we're talking about the null hypothesis in the context of a significance test, we either reject it or we fail to reject it. We never say we accept it. So the alternative hypothesis is the hypothesis that we hope to prove essentially. And the alternative hypothesis says that the value of the population parameter is not equal to the value that the null hypothesis says it is. So if, for example, the null hypothesis is that the parameter of the population is 0, then the null hypothesis can be that either this parameter is not equal to 0, it's less than 0, or greater than 0. And that's the hypothesis that we're essentially hoping to prove. That being said, in the two examples, in the market share example, we mentioned that before the campaign was launched, the percentage market share was 10%, and we want to examine what the market share looks like after the campaign. So the null hypothesis is that the market share is 10%. This would mean that after the campaign, the market share has not changed. In the bottling machine, we want to run a quality control, and we mentioned that the actual quantity that needs to be in a bottle is 355 milliliters. And if the actual quantity bottled is different than this, then there is an issue. So in this case, we say that the null hypothesis is equal to 355. And in the market share example, the alternative hypothesis is that the proportion after the campaign is larger than 10%. We wouldn't expect the campaign to have reduced the proportion, so the null hypothesis is that the new proportion of market share is higher. And in the bottling machine example, we're using the inequality sign because we want this quantity to be exactly this. So if it's smaller or larger, then this is not good. So this is the alternative hypothesis for its example. And here is again the framework. Let's revisit it now that we've covered a couple of examples. So we need to identify the null and the alternative hypothesis, and we need to collect enough data to compute what we call the test statistic involved in the hypothesis. So all hypothesis tests, they make some assumptions, and once you collect the data, you use the data in order to form a test statistic. So the test statistic is different for each hypothesis test, and if you want to understand the test in depth, then you actually need to go through all the formulations. But irrespective of what the test statistic looks like, all tests, in the end, they produce something called p-value. So we assume the null hypothesis is true. This is it according to a framework, and the p-value is essentially the probability that the null hypothesis is true. So if the p-value is very small, then we believe that there is sufficient evidence to reject the null hypothesis and go for the alternative hypothesis. If the p-value is not small enough, then we do not reject the null hypothesis. And again, accepting the null hypothesis is not something that we are doing. We can't say this. So the p-value is defined as the probability of finding the observed or more extreme results when the null hypothesis is true. So what does this mean? So we have a sample of data collected from our population, and we're interested in a specific parameter. So let's assume for a second that the null hypothesis is true. If the null hypothesis is true indeed, what is the probability of having observed this kind of value for the sample parameter, or a more extreme value? So let's take a look at this picture here. So according to our null hypothesis, for example, our data looks like this, it's distributed like this. And then we collect a sample and we find that the value of the parameter is, let's say, here. So if the null hypothesis is true, we would expect the parameter to lie somewhere around this region. However, we've seen that the value of our parameter is, according to our sample, around here. So this means that if the null hypothesis is true, that's a very, very, very unlikely event. Therefore, if the p-value is very small, then we reject the null hypothesis and we're saying, look, if the null hypothesis was true, then I should have observed something around this region, and I observed something around this region, which is very unlikely. So we reject the null hypothesis. And as I mentioned, all the hypothesis tests, they produce a p-value. It doesn't matter the kind of hypothesis test you're using, which is very convenient because even if you don't fully understand how a test works, if you know the assumptions of the test, so that you're making sure you're using it in the correct context, then you can interpret the results based on the p-value. And these are the standards that are followed more or less. If the p-value is less than 1%, then the test is definitely significant. If there is between 1 and 5%, we say there's strong evidence to support the alternative hypothesis. Some people accept significance at p-values between 5 and 10. We might say there is weak evidence to support the alternative hypothesis. And if the p-value is above 10%, then we definitely are not going to support the alternative hypothesis. And this is more or less a standard. That's so standard that even in R, when you run a hypothesis test, R is helping you out essentially. It shows you in the interface whether a test is significant or not. So quite often it won't even let you interpret the p-value yourself. It tells you, hey, this test, there's very strong evidence to support the alternative hypothesis. Another important concept around this is what we call the significance level. So the significance level is the probability that the test statistic will fall in what we call the critical region when H0 is actually true. So what this means is you saw earlier that when you have a null hypothesis, you assume that data is distributed according to some way, and if the p-value is in the extremes, then this essentially means that under the null hypothesis, the probability of getting this kind of sample is very low, so we reject the null hypothesis. So if the p-value lies in this region, then we reject the null hypothesis. This region is determined by what we call the significance level. So in theory, if we wanted to do things the right way, we'd say that we predefine a significance level alpha before we embark on our journey to run the hypothesis test. So we most commonly say that alpha is at 5%. So if alpha is at 5%, then we draw on the distribution of the null hypothesis the rejection regions, and we say, okay, if the p-value falls in those rejection regions, then we reject the null hypothesis. Now, in practice, there are not many people who are doing this because the interpretation of the p-values has been more or less standardized on the slide I showed you previously. But in any case, it's good to know about the significance level. It's an important term in hypothesis testing, and you might encounter it from time to time. So you might hear people saying that we found the results are significant at the 5% significance level. So this means that the p-value was less than 5%. And this is a general framework for working with hypothesis testing. That's a very useful slide. It helps you understand how you can formulate the results. So depending on whether the original claim around the null hypothesis, depending on whether this claim contains the condition of equality, and depending on whether you reject or you do not reject the null hypothesis, then you are provided here with different formulations as to how to present results. So you can say, for example, that there is sufficient evidence to warrant rejection of the claim that if the original claim contains the condition of equality and you reject the null hypothesis, for example. So there are different kinds of errors that can take place when doing hypothesis testing. One kind of error is type 1 error, which is the error that we reject the null hypothesis when the null hypothesis is indeed true. So let's say you are in the context of a court of law, and if the jury convicts an innocent person, this could be a type 1 error. Type 2 errors exist when we don't reject the null hypothesis, which is false. This occurs when a guilty defendant would be acquitted. So the type 1 error is equal to the significance level. So if, for example, we have a significance level of 5%, which means we accept a p-value if it's less than 5%, this means that if we run multiple tests, 5% of the time, we're going to reject the null hypothesis when it is indeed true. We just had an outlier sample. And type 2 error is also the Greek letter beta, also signifies the power of a test. So a test that's very powerful will reject a null hypothesis that is false. So statistical power is a very important property of hypothesis tests. And some tests are more powerful than others. So this confusion matrix here summarizes type 1 and type 2 errors. As you see, this matrix here is similar to the confusion matrix you will encounter in a machine learning setting. Essentially, you care about rejecting the null hypothesis when it's false and accepting it when it is true. So in the machine learning literature, type 1 error is also called the false positive, and as I mentioned, it's represented by the Greek letter alpha. And the type 2 error is called a false negative and is represented by the Greek letter beta. So let's see this example. Let's say that null hypothesis is that the defendant is innocent, and alternative hypothesis is that the defendant is guilty. So what is the type 1 error in this case? Think about it. And what is the type 2 error? Well, a type 1 error, as we mentioned, is a false positive. It's saying that someone is guilty when they're indeed innocent. And a type 2 error would be the opposite, saying that someone is innocent when they're really guilty. Now, which error is more important? This depends on the context, as with all things. This is a cost-sensitive example in the sense that for some cases, maybe the false positive is more important than a false negative and vice versa. So if, for example, the cost of someone being guilty is that they have to pay a small fine, and we did a mistake there, then this might not be such a big deal. But if the cost of someone being found guilty when in reality they're not, and then they go to prison for life, then this is a much more serious case. So really, the kind of error and which one is most important really depends on the problem. So now let's see an overview of the different kinds of hypothesis tests. We have two types of tests, parametric and non-parametric tests. So in parametric tests, we make an assumption around the underlying distribution of the population. So this is a reasonable idea, and as we saw earlier, in statistics we're using distributions in order to model uncertainty. So we assume that our population follows a particular distribution, and then in the test we estimate the parameter of this distribution. So this works fine. However, in some cases, we might encounter datasets where they do not seem to abide to any particular distribution that could be used in some test. So what can we do in that case? Well, in that case, we can use non-parametric tests. These are tests which make looser assumptions. They don't assume that the data follow a specific distribution, but they might just assume that the distribution is unimodal, for example. So as long as it is unimodal, it doesn't matter whether the data is coming from a Gaussian distribution or a student's t-distribution, everything's fine. However, the issue with non-parametric tests is that they are less powerful, so we're more likely to get a false negative. It might be more likely that these tests do not manage to reject a null hypothesis that is indeed false. However, a common assumption amongst nearly all of the tests, except for some very sophisticated tests, is that the samples are independent and identically distributed. That is, one sample does not influence another sample. So we have a collection of random samples from the population. There are certain cases when this is not true and we need to be very careful. So a case where this is definitely not true is in datasets where there's the notion of time, for example. So if you want to conduct a test around the price of a stock in the stock market or the demand of a product, if you have time spans which are very close to each other, let's say today and tomorrow, then there's going to be high correlation between those values. So there are certain techniques you can do in order to fight against this issue, which we will not cover right now. In general, in hypothesis tests, you have to make sure that the samples have been collected randomly and they're independent and identically distributed. This also means that some parts of the population will not be overrepresented. So if, for example, you are in a country and 50% of the population are male and 50 female, this should be represented in your sample as well. So here is a list of the most commonly used tests in practice. I've broken this down for you in parametric and non-parametric tests. And these are the tests that you're going to encounter most of the time and the tests that you're also going to use most often if you ever have to use a hypothesis test. So let's see when you can use them and under what circumstances. The z-test is a test for the mean of a population or two populations. So using a z-test, we can test, for example, that a parameter of the population, let's say the height, is equal to some value. Or we can take two different populations, let's say males and females in a country, a test for the quality of a parameter, for example, their salary. Something else we can do, and that's why I mentioned that we might have paired or unpaired samples, we can also take a group of people, measure something on them, and then make an intervention and then make another measurement. This is the case for paired samples. So for example, if we're in the domain of medical research, we might take a group of people, measure their blood pressure, then give them some kind of medicine and then measure their blood pressure again. So this would be a case of a two-paired populations because we have exactly the same people before and after with an intervention in the middle. So the z-test, as you might realize, it's quite useful because the mean is one of the most important parameters in the population, and differences in populations, whether they're different groups or the same group in two different points in time, these are scenarios that occur very often in practice. However, the z-test has a drawback which the t-test solves. So the z-test assumes that we know the variance of the population. However, in practice, this rarely happens. So this is what the t-test is doing. It's like exactly the same, but you can use it without knowing the variance of the population. So whereas the z-test is in practice the first test to be taught to statistics students, the t-test is actually the one that's used. Then we have a similar kind of test, but for proportions, which is simply called the test of proportions. And we also have ANOVA, which is like the tests above, but for the means of multiple groups. So maybe we have 3, 4, 5, 6, 7 different groups. And ANOVA also has different versions of it, such as two-way ANOVA and one-way ANOVA, where in two-way ANOVA, we can again compare between multiple groups, but also use two variables instead of just one. This is covered in more depth in the additional content section. In the non-parametric tests, we have equivalence of the parametric tests, but with less assumptions. So the sign test examines the differences between the two populations. The Wilcoxon and Mount-Whitney tests, they're exactly like the t-test, but they make looser assumptions. And the Kruskal-Wallis is exactly like one-way ANOVA, that is, it examines the differences between the means of groups for one particular parameter, but once again, it makes looser assumptions. So let's look into these tests in a bit more depth. We can use the t-test, as I mentioned, when we have two groups. These groups can either be paired or unpaired. So two groups are paired when we essentially have the same group of people before and after, with an intervention sitting in the middle. And the variable of interest is numerical. So this graph here shows when you would use t-test. You have two groups, a numerical variable, and you've used the box plot to visualize this, and you suspect there are differences between the means of the two groups. Now, what you should do in order to perform a t-test is to make sure that the underlying distribution of the data is normal, and also that the variances of the two populations are equal. If these assumptions do not hold, then we can use the non-parametric alternative, the Wilcoxon-Mann-Whitney U-test, that assumes that the distributions have the same shape, but they don't have to be normal. They don't even have to be symmetrical. However, this test is a test for the medians of the distribution, not the mean. So be careful when reporting results. The test of proportions, also called the two-proportion Z-test, is like the t-test but for proportions. We should have at least 10 successes and 10 failures in our sample, and the population in each group should be at least 20 times as big as its sample. The reason is that the test of proportions is based on an approximation, so we convert the proportions to the normal distribution if you look at the formulation. So in order for this approximation to be correct, we need to have a large enough population, a large enough sample. And ANOVA is a bit like a t-test, but with multiple groups. So let's say that you had three different groups, as we see in this case. This is from the famous iris dataset, and we have three different flower types. And you want to compare the means for a variable, let's say sepal width, amongst the different groups. So you've created a box plot, you have one box per group, and you can see the values of the box plot on the y-axis, and it's clear that these two groups seem to have similar values, but this one stands out from the rest. So ANOVA can test this for you. ANOVA will tell you whether all the means are equal or not. The reason we're not doing multiple t-tests, because in theory we could do a test against this for this, this for this for this, etc., is that this would have an inflated probability for a false positive, a type 1 error. So this is an issue. Hence, the correct way to do this is to use ANOVA. If you remember when we were talking about tests in general, we were saying that the significance level, which is usually at 5%, is the probability of getting a false positive. That's why if we conduct multiple t-tests between all the different combinations of groups, it's very likely we will get a false positive. Whereas if we conduct an ANOVA test, we will test for the equality across all groups at the same time. So the assumptions behind ANOVA are like a generalization of the assumptions of the t-test. We assume the underlying normality of the population and that the variances are equal. If the assumptions are not being met, then we can use a Kruskal-Wallis test that, much like the non-parametric alternative for the t-test, assumes that the distributions have the same shape. And talking about assumptions about the t-test and ANOVA, how can you test for these assumptions? Well, regarding normality, there are various tests such as the Shapiro-Wilk or the Kolmogorov-Smirnov test, and there are many more normality tests with slightly different power and slightly different performance depending on the circumstances. In practice, the Shapiro-Wilk or the Kolmogorov-Smirnov test should do most of the time, and can also test for normality using graphical means, specifically using what we call a QQ plot, where we present the data in a format of the quantiles of our sample versus the theoretical quantiles coming from a normal distribution. You can see this plot here, and if the data is normally distributed indeed, then what we should observe is that most of the points fall on this straight line. This in practice is a test that's very easy to do. You can just run a QQ plot in R or Python, and if you see the data falling on a straight line, it's safe to assume that they must be normally distributed or close to it. But obviously, if you want to be sure, the best way is to actually do a hypothesis test. And for equal variances, there are again various tests. The two most famous ones is Bartlett's test and Levin's test. Bartlett's test is the most common one in practice because it's more powerful if you assume that the distributions are indeed normal, which is what you want for the ANOVA test and the t-test. Levin's test is a hypothesis test that is more powerful than the Bartlett's test when the distributions of the data start to deviate from the normal distribution. They're not so close to the normal distribution anymore. So before you embark on a t-test or an ANOVA test, run the following. Run a QQ plot, run a Shapiro-Wilk test, run a Bartlett test, and see whether these tests are significant or not. So in this case, you want the tests to not be significant because the null hypothesis tests for equality of variances or equality to a normal distribution. And if these tests fail to reject the null hypothesis, then you're good to go.